Okay, so now we are recording. We are recording, and as you recall, uh, there are integrals such as this integral here, the integral from 1 to 2 of e to the 1 over x power dx, that you cannot find you can't get the exact answer for, because there's no antiderivative for e to the 1 over x power. And so we learned that we can basically, the idea from Calculus 1, where we choose rectangles to be, we can add the areas of rectangles to approximate the area of the integral, to approximate the definite integral, which is an area. Okay, so what we did, let me bring up the ebook here, one moment. Let me get that up right now, actually. One moment. Let me do that here. Okay, one moment, I'm just bringing up the ebook. So we had talked about this before, but I'll just, where's the ebook? I want the, hold on, that's not what I want. One moment, I just got to get it. So we'll address exam questions a little later in class here. Okay, so there is approximate integration, and we learned, for instance, that like in figure 1, we could approximate the area underneath a curve, or I should say really the integral. But the integral is, the definite integral is the area between the function and the x-axis from limits a to b. And, you know, we could use left endpoints to determine the heights of our rectangles, as you see in figure 1a. We could use right endpoints to determine the heights of our rectangles, as you see in figure 1b. And then in, you see here, in figure 1c from section 5.9, we could use midpoints and to determine the heights of the rectangles. Now, also don't forget, we have a trapezoidal rule approximation that we can use, where we use trapezoids instead of rectangles and add up the areas of the rectangles. And there's even another approach called Simpson's rule. Simpson's rule, what you're going to do is you're going to, hold on here, let me get that off. In Simpson's rule, you're going to utilize, well, to approximate the areas under the curve, you're going to utilize parabolas to approximate the function over the different subintervals, and that's actually usually a more accurate approach. Now, all of these methods have formulas that go with them. And actually, hold on just 1 minute. Let me bring up the formulas. The formulas for the approximate integration are in our textbook. They're in the textbook in section 5.9. Okay, they're in there. But you know, under course content in chapter 5 for section 5.9, there's a link that will bring up my my sheet that I prepared that puts all these formulas all in one nice place. Okay, how many maybe have downloaded that sheet already? How many have downloaded that? There's probably some of you that have. Okay, good, Taj, good, excellent. Good, Jan. Wonderful. And so, you know, you have a formula for the trapezoidal rule. You have a formula for the midpoint rule. You have a formula for Simpson's rule. And the left endpoint and right endpoint rules, those you can just intuitively do, okay? And incidentally now, what is of interest is for all of these rules, these approximation rules, they're used to approximate definite integrals, but then they're approximations, so there are going to be errors, right? Because an approximation to a definite integral is not the same as the value of the definite integral. So it's very nice then for all of these approximation formulas to have error bounds. So like for instance, the trapezoidal rule, what would the error bound be on your approximation using the trapezoidal rule? Well, according to this formula here, the bound on the error, the E sub t, is the absolute value of the error. That would be less than or equal to this value, big value k, which I'll show you how to get, times the quantity b minus a cubed. B and a are your limits for your definite integral. And then over 12n squared, n is the number of subintervals. So these formulas, all of these approximation formulas, well, the trapezoidal rule, midpoint rule, and Simpson's rule have these error bounds. And it's very important to find error bounds so you have an idea of how good your approximation is. All right, so today we're going to be working with those error bound formulas. So now if we go back to the problem here. So again, we wanted to use the midpoint rule to approximate the integral, and n sub 10 means 10 subintervals. And so, you know, that was the first part of the problem. All right, so what we did was there's the formula sheet, and here was the, interval from 1 to 2, and each subinterval had a length of 1/10. And so for every subinterval, we identified the midpoint. So like for instance, the first subinterval going from 1 to 1.2, 1 to 1.1, the midpoint was right here. Well, that value of that midpoint is 1.05. The second midpoint between 1.1 and 1.2 has a value of 1.15. And so you see, we take these values of x and we substitute them in the formula, and we do that for all 10 midpoints. And then we use the midpoint rule, which again, that's given here. Okay, that's given here, but it's a formula, but intuitively you know what you're doing here. But it's there. You use the formula to compute. You use the formula to get the approximation, and then you have to go into like Desmos, as I showed you, to find the answer. Okay, because WebAssign's not going to just take any answer. It wants the answer that's found by doing this computation. Okay, and so there it is. So we found that the definite integral was approximately equal to 2.019101885. Okay, that would be correct to, or rounded, let me see here, 1, 2, 3, 4, 5, 6. So it's like to 9 decimal places, right? So, okay, that's great. Now, how accurate is this approximation? How accurate is it? Okay, well, that if we go back to our this example that you copied down from the last class, and everything I've talked about, we talked about in our last class, and it's the last recording for this example. Now the next step is, now that we have our approximation, we want to estimate the error of this approximation. How good is our estimate? How good is it? Is it as good as we want? Do we need to take more subintervals to get a better estimate? Okay, we really need to have an idea. So now let's continue the problem. We have our approximation for the definite integral. How good is the approximation? So now we move on to the next step. We want to estimate the error, the absolute value of the error, E sub m of this approximation using the formula. Now this formula, let me just go to the formula sheet so you can see it. This is the formula we're using right here. Okay, that's the formula we're using from section 5.9. And let me just see here, one moment. One moment. All right, so the E sub m here, the E sub m would be equal to the approximation, in this case m sub 10, minus the true value of the integral. That's what E sub n means. And on the right-hand side here, this is a bound on the error. So we know what B is. B is 2, A is 1, N is 10. We know that because we're using M sub 10, midpoint approximation with 10 subintervals. What's left to find is this value of K. Now the value of K, according to the formula sheet, the value of K would have to be greater than or equal. Okay, here's the criteria. The value of K, big K, would have to be greater than or equal to the absolute value of the second derivative of our function over the interval from A to B. Okay, that's the criteria. So, and that can be proven. If you, in graduate school, I took a numerical analysis course, and we actually proved that formula. We actually proved this result here along with this criteria. So they don't prove it in the book that I know of, but if you continue on in your math career and take numerical analysis, it's likely you'll see a proof of that result. So, okay, well, now here is the error formula. And let me give you a moment to copy down up to here. All right, so please let me know if you have any questions. So now you're continuing the example. We're continuing the solution to the example. Okay. So this is just a continuations of your notes for this example from last time. Okay, so everything in the error-bound formula is determined except this K value. We have to find the K value, and we're told that the K value that we want to find has to be greater than or equal to the absolute value of the second derivative, okay, of our function over the interval from 1 to 2. So, well, our function is equal to e to the 1 over x power, which is also e to the power x to the negative first. I write 1 over x as x to the negative first because it's easier to differentiate that. It's easier to use the power rule, in my view, than the quotient rule. Okay, but we are going to have to use the chain rule here, right? We are going to have to use the chain rule. So the chain rule, all right, well, we have e to the power x to the negative first. So what's the outer function? What's the outer function? So e to the power x to the negative first. If we're going to use the chain rule, we need an outer function and an inner function. What would the outer function be? It's sort of obvious, but I'm just asking. That's correct, Taj. It's e to the power u. That's right. That's the outer function. So we differentiate. What's the derivative of e to the u's power? Well, the derivative would just be e to the u. So using the chain rule, the derivative of our function is e to the power x to the negative first. Then we take the derivative of x to the negative first, and that'll get us negative x to the negative second. And that gets us our first derivative. Now the second derivative, what I do for the second derivative is this minus sign here. This minus sign, I'm gonna pull that out in front before I take the derivative. You know, the negative can be factored out in front of the derivative sign. And so what I have to do is I have to now differentiate x to the negative second times the e to the power x to the negative first. So of course, that's a product. We have to use the product rule along with the chain rule. And that's laid out here for you. That's laid out here for you. So this is like you know, f prime g plus f g prime. Okay, where let me just see. Sometimes students, they get a little nervous when they have to take a derivative, but like a product, but it's no big deal, right? No big deal. So this is f prime. This is g. Plus, then we got f. And then this whole thing here is g prime. No big deal. So what we end up getting then is this expression here for the second derivative. Are there any questions up to here? All right. Well, if you're good with that, then we have to analyze this second derivative. So I'm going to write it in a way that helps me analyze it. It's a lot like in calculus 1. Remember when you would have functions and you had to determine whether they're concave up and concave down and all that, and the mins and the max. You wrote your derivatives in factored form. How many can recall that from calculus 1? For polynomials and certain kinds of functions, you always try to get that in factored form. Taj and Mario remember that, and Ange and Sandia, absolutely. So same kind of thing here. I have this derivative. It looks kind of ugly, but look, I have a common factor of e to the power x to the negative 1. That's a common factor, right? And I'm going to factor it out. And so I'm going to have e to the power x to the negative first times then 2x to the negative third plus x to the fourth. Well, I'm going to write 2 times x to the negative third as 2 over x cubed. and x to the negative fourth is 1 over x to the fourth. Okay, and I'm going to just, then write this, and I guess this got cut off a little bit, but I can write it here. This is going to be e to the power 1 over x times 2x plus 1 over x to the fourth. Okay, so that's a pretty good form for my derivative. That's a pretty nice form to get it in. So I just rewrote what was at the bottom here. Are there any questions? All right, well, so now what we have to do, of course, one moment here. Yeah, what we have to do is now we have to find out where the absolute value of this second derivative is maximized over the interval from 1 to 2. So I will go to the next page. Here again is our second derivative in very nice form. And because like you have this exponential function, okay, you have this exponential function here, and then you have the 2x plus 1 over x to the fourth there. Well, over the interval from 1 to 2, the absolute value of that second derivative would just be the second derivative. That second derivative is positive. So I can write the absolute value of the second derivative just as e to the 1 over x power times 2x plus 1 over x to the fourth. And that second derivative, it turns out it is a decreasing function over the interval from 1 to 2. It is a decreasing function. So you could do that, you could learn that by graphing that second derivative in Desmos, for instance, and you would see it decreases from 1 to 2. Okay. But it's decreasing function. So now the question is, if I have a decreasing function, okay, okay, so let's just say my function looks like this. Let's say, I'm sorry, my second derivative. The absolute value of my second derivative is decreasing. And it's decreasing from 1 to 2. Okay. Well, where would the second derivative, and this is the x-axis and the y-axis, where would the second derivative be maximized? Would it be maximized at x equals 1? Or would it be maximized at x equals 2? Where's the second derivative, or the absolute value of the second derivative? Where is it maximized?
X equal 1.
That's right, Ange, and that's right, Touch. X equals 1. It's highest there. So this means then that since the second derivative is maximized at x equals 1, the k value would have to be greater than or equal to the absolute value of the second derivative at x equals 1. So to determine the k value, when I want the k value to be like, it has to be bigger than or equal to the absolute value of the second derivative. at 1, but you know, I'm going to make it equal. You know, I want K, my error bound, I want the error bound to be small. I don't want it to be unnecessarily large. So let me pick the smallest allowed value of K. Well, the smallest allowed value of K would be the second derivative evaluated at 1. And if I put 1 in for X in the second derivative, I'm going to get 3e. And so therefore K is equal to 3 times E. That's what K is equal to. Right? So now again, the error bound, the bound on my error using the midpoint rule approximation. Okay. Well, I want to be careful. The bound on my error is now this. Okay, it equals that, exactly that. So the 3 over 3 times Z is the big K value. Maybe I'll just write it out this way. The 3 times Z is the big K value. 2 is equal to B. 1 is equal to A. And then, of course, 10 is equal to N. So the exact value would be 3e over 2400. Now, maybe WebAssign would say approximate, or e over 800. If WebAssign said approximate your answer to 7 decimal places, it would be 0.0003398. So we can say that our approximation, and let me see, our approximation, if you recall, for the midpoint rule, using 10 subintervals, hold on here. Hold on, let me do this again here. So this is separate from what I'm doing here. So if I take the midpoint rule approximation, which, as you recall, was 2.019101885, and I were to look at the difference between that approximation and the true value of our integral, which only God knows, so to speak, or, you know, whoever you believe in, Buddha, whoever you believe in. Okay? The difference, the error between the approximation and the true value is going to be less than or equal to 0.0003398. Okay, so the question is, are you happy with that approximation? If you use this approximation for the definite integral, you could be off by a little more than 3 10,000ths. Okay, are you happy with that? Okay, well, if you're doing calculations for like astronomy, you would definitely not be happy with that. You have to be very exact for astronomical calculations. So how would you get a better estimate for the definite integral? What would you have to do using the midpoint rule? What could you do to get a better estimate? That's right, Mario. Use more points. Use more and in fact, that means then use more subintervals. So using more subintervals works. Of course, the cost is it's more computation. And this is very relevant to computer science because you might need to have a midpoint rule approximation where you have 1 billion points to get the accuracy you want, maybe 1 trillion, who knows? And that's going to take computer time. Now computers are pretty fast these days, but things do still take time, right? So this is the kind of thing that is very relevant. Or to computer science, for instance. Are there any, who's a computer science major here? Do we have a few of them in the room here? Okay, Javier, and Ange, and Taj, and Jan, and Jingson. Wow, okay, great. All right. Well, are there any questions now up to this part? Okay, Sandy is a bio major, and I assume the rest of you are science majors, and I don't mean to leave you out. Science and math majors, engineering majors. This is relevant to your professions as well. Mario's engineering. Yeah, absolutely. So, all right. Well, absolutely, Sandia. Science and math are related. You can't do science without math. Absolutely. We wouldn't be where we are today in terms of progress and so forth without math and science, right? So on the calculator, this would just be E divided by 800. So you take on the calculator, you would just take oh, I see what you mean. Yeah, I guess on the TI-83, it would be E to the first power divided by 800. That's right. Well, so Mario, you could increase your level of accuracy on your TI-83, 84. If you go to mode, and there's a thing for float. I mean, I think on mine, let me try real quick here. Let me type in E to the first power and divide that by 800. Hold on here. One moment. E to the first power divided by 800. Yeah, I get this. I mean, I round it in the 7th decimal place. So check your settings on your calculator, okay? And Mario, we can chat about it after class, okay? If you keep trying to get that answer. All right, so now another question is now we've satisfied of the 3 questions. We have done the first question, and then we've estimated the error of our approximation. Now we might want to know, is this approximation an underestimate or an overestimate? And for simple functions, for functions that are either concave up or concave down, this is a very doable kind of question. So if I look at the second derivative, okay, if I look at that second derivative again, okay, here it is. Well, over the interval from 1 to 2, we determined that the second derivative here was positive, right? Well, when the second derivative is positive, I mean, this is greater than 0, when x is between 1 and 2. When the second derivative is positive, what does that tell you about the concavity of the function? With the concavity of our function f of x equals e to the 1 over x power, is that function concave up? Is it concave up, or is it concave down? Which is the right choice? based on the fact that the second derivative is positive. Think back to calculus 1. Concave up. Good. Good, Taj. Good, Javier. It's going to be concave up. So this function, it's a concave up function. And what I can do is I can draw a picture here of a concave up function. Okay, concavity. That's right. That's right, Sandia. We're talking about concavity. This function here, and I'll just, let's just say, this is our function, e to the 1 over x. It's a concave up function, and it goes from 1 to 2. So I want to be a little careful what I write here, but I'm just looking here. I'm just looking for this function. Maybe let me just write it again. F of x equals e to the 1 over x. I'll tell you what, let me give you a moment to copy the picture down, okay? Let me give you a moment here, and then we'll talk about this. Okay, so what I'm doing here is, as you know, with the midpoint rule, we're adding a bunch of the areas of a bunch of rectangles up, right? A bunch of rectangles based on our subintervals. Now, what I am going to do is I'm going to look at a typical rectangle. So this here is one subinterval going from this point to this point. And right here in the middle is the midpoint, right? This is your midpoint. Okay, so every rectangle using the midpoint rule is going to resemble this rectangle. Okay, with the midpoint of the subinterval determines the height of the rectangle. And what I'm doing here is I'm drawing the height of the rectangle. The height of the rectangle, the rectangle, of course, this here is all good area, right? This is all good area. All right, and we gain some area here, right? This area is gained area that we don't want. We don't want that gained area because that area is not under the curve. Okay, but over here, this area here is under the curve, and so that's the area that we have lost. Okay, so the midpoint rule approximation, we're going to lose for every rectangle, we lose some area that we want, and we gain some area that we don't want. Well, if we look at the difference, between the lost area and the gained area, if we look at the difference, is the lost area minus the gained area, is it less than 0? Is it negative? Or is it positive? Based on this concave up function. Does the blue lost area, right, so the lost area minus the gained area would be negative. In other words, we lost more area than we gained. We lost more good area than we gained like bad area. And so that's going to cause our approximation to be an underestimate. Whatever the midpoint rule is going to give us, the approximation, it's going to be less than the true value of the integral. So, like for instance, in this case, the midpoint rule approximation n sub 10 would be less than our integral. It would be less. Are there any questions on that? All right, well now, what do you think if we had a concave down function? Okay, I'll go to the whiteboard here and draw a sample concave down function. Is everybody good here? Want to make sure I'm pacing myself well. All right, let me go to the whiteboard. And let's see here. So we'll have to. Okay, this is X, this is Y. Here's a whoops, hold on. See, I got to take this, I got to put the pen back on. Here's a concave down function like this. And let me go back here. Not perfect, sorry. But, all right. This is recorded. Yes, Sandhya. This is recorded. Okay, you're welcome. You're welcome. All the recordings of the lectures can be, of course, found in the Blackboard Collaborate Ultra under the menu, and then, of course, if under the course content, I also have the recordings with closed captions in there. So here's a subinterval. This is the midpoint. The midpoint, the value of the function. This is this function here. F of x is concave down. And we have, let's see, maybe I can put this in green. Let me see here. Yeah, so I want to say this the right way. So this here is gained area. Gained area in the approximation. And then over here, this is the lost area. So the approximation did not capture that lost area. Well, if we take the gained area and subtract the lost area, is that gained area minus the lost area positive or negative? Positive, and you can even see it. You can even see it. That's right, Tuss. That's right, Ian. So that area is going to be positive. So what's happening is the midpoint rule approximation is overestimating the area underneath this concave down function. It's going to give you, if you take the gained area minus the lost area, for every rectangle, you're going to have positive. It's going to be positive. So the overall estimate here, the midpoint rule estimate is it's an overestimate. And you have to be careful in WebAssign for these kind of problems. Usually these conceptual problems, you get like one try to get the answer right. Okay, so you have to be careful. Okay, are there any questions? All right, I'm going to stop the recording. I want to do a another example with you. If it's really a follow-up to this one, but I want to stop the recording for this.